Hello everybody and welcome to session number 18 of my lecture on statistical energy analysis and hybrid methods. This session will be a very short one, but it will be a very important one because this gives an example of the so-called diffuse field reciprocity relationship. This relationship relates the energy in a diffuse wave field to the excitation at the boundary of such a field. And this is done here in this short session based on the classical diffuse, acoustic diffuse field, as it's well known from room acoustics. So we start, as we are talking about 3D diffuse acoustic fields, we take the three-dimensional formula, which is given by this equation 193, and we use the pressure that's representing the amplitude. All our consideration takes the same time, so delta t is equal to 0. And if we do so, we get this expression here. There's some small changes. This is the azimuthal angle goes from 0 to pi because we're just having a half space available. And we have the extra pressure because the pressure at the surface is the pressure itself plus the reflected one, that's adding up at the boundary. In the next step, we are replacing the probability function by the room angle, which is given by this 1 divided by 4 pi, and the sine component, which is also belonging to this probability function. We have introduced the reflection factor. Everything that is not dependent on the angles is outside of this integral. And obviously, the azimuthal angle can be taken out. This is why we just find the pi here. The remaining interval can be solved quite easily, and the result is the sinc function, which is the well-known cross-correlation function for diffuse sound fields, for three-dimensional diffuse sound fields. When we consider a rigid wall, this factor becomes 2. And on top of that, we can express the pressure field amplitude in terms of volume and energy. So we know that's a relationship between the energy and the pressure, and this is given by this expression here. The 2 comes from the fact that we are considering not a root mean square value, but we're talking about an amplitude. Good. If we're collecting all these things together, there's just one additional thing that is important to be used. We have to get rid of this volume. However, we can express the volume in terms of the modal density. And if we take the simplified version of the modal density expression for three-dimensional subsystems, it's given by this. So we are neglecting all the surface and perimeter extensions to correct this modal density formula, which is okay because all this can also be done when we assume a perfect diffuse sound field. And all the other parameters, like the surface and so on, in this modal density expression are there to consider the modification to a not that perfect diffuse sound field. So that's absolutely fine to stay with this one. If you do so, the pressure is then related to the expressions that are defining the property of the fluid, frequency, and the energy. This gives the pressure that we would later lead in this expression of the above version of the cross correlation. And if we do so, we get finally the cross spectra of cross spectral density, because the omega, so the spectrum, is hidden in the k term here. And that's quite a reasonable, simple function. So we need the energy, the modal density. We have an expression of the distance of 2 points at the boundaries. And this gives us the cross-spectral density for 2 measured pressure positions at the boundary with distance delta r. Okay, what is this useful for? Next step, we go to a discrete version of this. So it means we take, for every pressure, we assume that we're just using a discrete version with a specific element area delta S. And then this helps us to change the pressure formulation to a blocked force. So because pressure times the surface gives us the force that is exciting the boundary. And if you do so, we get again this expression where we have a delta S square here on top of this formulation. So this is a discrete form of two elements on a regular grid with such element sizes. Okay, so this is the excitation part. So in contrast to this, now let's have a look at how would the radiation, the discrete radiation be if we would radiate into half space. And here we are again considering a regular grid. Just assume that we have one node here where we have to consider this area, and this is vibrating with this velocity. And the vibration of this element excites a pressure, because there's an acoustic wave field on top of that, at the distance delta r, which creates a pressure here. And this pressure can again be used with the surface area to create a force out of it. The propagation of the velocity term here to the pressure here, that's given by the classical point source function, but the point source function for half space. So this is why we find a 2 here and not a 4. So this is takes care of the half space and then the usual formula. And the pressure is given by exactly this formula. And if you remember well, the surface multiplied by the velocity, this is equal to the source strength Q from the former considerations. And the delta R is just the distance between the two nodes in the mesh. Good. If we use this expression here on top, so we just multiply again by this delta S as given here, then we can create the mechanical transfer impedance for this. So that means that the force exciting this is related to velocity at the other position by the above given expression, finally ending up with this. So that means we are quite near to our final expression. The last step then is that we take just the real part of this. When we're taking the real part of this, we get a reading of the cosine function together with this complex number. The sine function is the important one. And if we are arranging all these things together, the real part of this, we will finally find that this is the expression of the real part of the mechanical transfer impedance. So we have the sinc function here, we have again some expression here, and we have the squared surface of the squared area of our element of the regular mesh. If we now finally compare it to the above equation and enter this and rearrange the terms a little bit, we are finally ending up with the so-called diffuse field reciprocity relationship for a three-dimensional acoustic wave field. What is it saying? It says that the cross-spectral density of 2 points at the boundary of a diffuse sound field, it could be a wall in a church or a wall in a room, at distance delta L, is just given by the energy, the modal density, and the mechanical transfer impedance, or as we say, the radiation impedance of the half space into the free half field. That means a very complex term that has to be calculated by many statistics of several waves can now be given by a relatively simple expression: energy, modal density, and the radiation impedance. And this is extremely helpful because it's, let's say, it simplifies all exchanges of energy or excitation of reverberant field of any connected boundary or well-known deterministic boundary. So that's the reason why it's absolutely the baseline of hybrid methods, as you will later see in other examples. Good. So thank you very much for this very short session, but please keep in mind that's a really important one. So the diffuse field reciprocity relationship, this is something that you will see a lot in the next slides, especially when we're talking about coupling loss factors. Hopefully you had some fun, enjoy, and see you for the next sessions where I would like to talk about the SEA system description. So what do we need to describe a single SEA subsystem, and what do we need to describe a network, or let's say a system of many connected statistical energy analysis subsystems. So see you later then for session number 19.